So one important paper is the paper by Stylegan et al. Improved Techniques for Training Gans. This paper proposed an architecture that achieved better quality with 128 times 128 pixels, so meaning higher resolution. And it also introduced the idea of feature matching, as discussed before. There was also an idea of a new objective function, and there was the idea of historical averaging. So one thing we discussed before is maybe the idea of using exponentially moving average to average the values of the generator as training continues, and using this exponentially moving average is an idea that can be used for any type of network. Another idea is the idea of one-sided label smoothing, similar to label smoothing discussed before, just in a special case where the discriminator output targets values as 0.9 for real. There's also an idea of virtual batch normalization that avoids the dependency of data on the same batch and reduces this dependency. For details of all these techniques, I would refer to the paper. Next, we would like to discuss the idea of conditional GANs. Conditional GANs come in multiple forms, and I think it is meaningful to distinguish conditional GANs that are conditioned on class labels and GANs that are conditioned on input images. So in this first version, we are going to discuss the idea of GANs that are conditional of class labels. So in order to train these conditional GANs, one needs multi-class training data. That means the images that are trained on need to have a class label. And one would like to use these class labels to control the output of the GAN. So as we will discuss in the figure below, we will augment the input for both the generator and discriminator with class labels. This thing was first introduced by Mirza et al. In the paper Conditional Generative Adversarial Networks. The updated equation for this two-player min-max game is shown below. Let's first look at the image at the bottom of this page though. The generator now receives two inputs. The first input, as before, is a random vector z, and the second input that is new is a class label y. And the class label in this example would be 2. That means that the generator should output a digit 2. And then the generator outputs an image. The discriminator also receives the same label y as input. Therefore, the discriminator not only has to check that the image is real instead of fake, or not only classifies images as real and fake, but also considers the class label. So it has to, the image has to conform to the class label y. So if the generator should generate a 2, but instead outputs a really nicely looking 5, the discriminator would still penalize the generator. So going to the equation then, the data is generated conditioned on this class y, and then the discriminator has to correctly discriminate the input data x that is conditioned on y, and what happens here in this equation is that the discriminator will be penalized for getting the label wrong. So for all the input data x sampled according to the data distribution, the discriminator needs to get the correct label. Also here we see that the generator has both set. So here we see some results of conditional GANs. Here we see that the given label changes, and going down, looking at different rows, we see different random vectors for the initialization. So what we can observe here is then going down one column, let's arbitrarily pick this column of 4s, that indeed, if a 4 is required, all the results look like a 4. And the same seems to be true for the other digits. So 9s all look pretty good. They all look like 9s. A very important class of conditional GANs are GANs that perform image-to-image translation. These conditional GANs learn a mapping from an input image to an output image. For example, the input image is a black and white image, or let's say a grayscale image, and the target image is a colorized version of the image. So the generator would learn how to colorize a black and white image. And the discriminator tries to learn to differentiate between real and fake colorizations. For these type of traditional conditional GANs, the architecture changes, in my view, are much more significant. It's not only like one digit gets, one value gets inserted somewhere, but really here the generator network starts looking a lot more like an encoder-decoder architecture. Now, there are a lot of these image-to-image translation tasks, and we see a lot of networks being proposed that are general type of networks, but we also see a lot of networks proposed very specific to one particular task. So let's just look at one such network as an example, but since there's so many networks proposed and these are not the latest ones, it's not that important to exactly understand how the network looks like. The most important thing when looking at this network is just to observe that the network is an encoder-decoder architecture. So as input, we get a grayscale image, and as output down here, we get a colorized image. Then looking at this particular architecture, we can see how first the encoder decreases the resolution from starting from 256 times 256 times 3. We see then 128 times 128 times 64. All right, so I'm not going to look at all that. Just as usual, a decoder, an encoder, and we can notice this particular encoder has a pretty small bottleneck. Actually, it goes down all the way to 1 times 1 times 512. This is not very typical in a lot of these tasks. What we can see with other networks, they might actually have only a few downsampling steps. Maybe they would go from 256 times 256 to 64 times 64, and then perform some upsampling. All right, but still, you can also look at the decoder. which kind of mirrors the encoder when you look at the different tensor shapes. One note at the end, there's one idea that's called PatchGAN, and instead of just feeding one large image to the discriminator, it's also possible to feed individual image patches to the discriminator, and maybe this way it's easier to handle large resolution images. Alright, this was just some random example. Let's now look at one very significant paper that had a lot of impact. That is the paper Image-to-Image Translation with Conditional Adversarial Networks. The authors propose multiple application scenarios. First, going from labels to photos, maps like Google Maps to satellite images, edges to photographs, and day to night photography. Here we see the examples. There's one data set for the segmentation of street view scenes, and this is popular for training these segmentation to color image translation networks. And on the top left you see one such example. Then you see aerial satellite image to map. Actually, you can train such a network in both directions. You can go from map to image and from aerial image to map. Here you see labels to facade. So there's a abstracted facade shown in a label map, and then there's a color image, colorization, grayscale image to color image, and on the bottom right we see edges, that is edges from a handbag, being translated to a color image of the same handbag, and then day to night translation. There's an interactive demo which we would like to try next. Naturally, translating edges to cats is the most important application. That's what people like to play with and then post pictures on social media. This is also how this paper got a lot of traction. Alright, let's see what we can do. We'll now modify the cat with modest drawing skills. Maybe let's make the ears larger. Looks more like a bunny, but what can you do? And then add two larger paws here. I don't know how to draw, obviously, so we'll just have to do with that. And then we'll see what happens. Alright, that was a huge success. Now we can go and maybe erase parts. Alright. Alright, let's erase this. And let's make more like some spherical cat. And then we'll want to have some tail here. Alright. Let's see what it does with this. Alright, so you can see lots of fun for people to play with. Also, you can play with facade labels to facade RGB image, edges to shoe. Alright. So we kind of skipped a lot of the details. We just want to look at these papers on a high level. Next, we want to look at this paper about multimodal unsupervised image-to-image translation. One problem with the previous paper was, first of all, the quality was not that great, and second, their input, so each input would only generate a single output. So what we would like to do next is have a generative adversarial network that can take one input and translate it into multiple other outputs based on some random vector. This is not because the previous paper couldn't or it didn't try to do it. I mean, they tried to insert some randomness, but it just didn't really work out. And the network that they trained ended up ignoring the random value that was used to kind of to entice the network to generate the multimodal output. But apparently it requires more than just injecting some noise. The idea of this paper is the following assumption, that an image can be decomposed in two parts. One is the content, that is domain invariant, and the other thing is the style, that captures domain-specific properties. The most important idea when thinking about content, that's at least what I do, is to think about pose. So maybe the approximate shape and pose of the head is the content, and then the style is what particular animal you are interested in. And in this example, we're doing translation from one animal to another. So for example, a wild cat will be translated to 3 different house cats. What we want to do is basically train some form of an autoencoder such that one image x1 can be encoded into content c1 and style s1, and another image x2 can be encoded into content c2 and style s2. So since this is the assumption that content codes are domain invariant, we see that the content space C is shared for both, let's call it image spaces of images, let's say wildcats, and then here we have another space of image of house cats. So the content space is shared that these images are embedded to, but then the style code, the style spaces, so S1 is the style space for wildcats and S2 is the style space for house cats. This is not shared. So what we can do here is, if we have one house cat, this image, let's say x1, and then we extract the content code and the style code, we can keep the content code c1 and combine that with multiple different style codes of some house cat here in this style space, and then generate new house cat images. All right, let's look at some examples. This is an input house cat, can be translated into these 3 big cats. And the big cats, this one here, can be translated into 3 house cats. Now, it is up to you to try to think about what content is being preserved here. So I would say mainly the pose. So we can see that in this left example, the house cat is looking straight into the camera, and what we see here in this example B, this big cat is slightly looking to this here, and then it seems that the head pose is quite similar in the other images. We can translate the cat to multiple dogs, and we can translate the dog to cats. And again, if you think about what is preserved, then I would say mainly the pose. However, this dog here also has quite distinct ears, and it seems that also these cats seem to preserve somewhat like this ear shape. So maybe more of the whole head shape is actually preserved than just the pose. On top we see translations for summer to winter, and on the bottom winter to summer. Another really remarkable paper is in Stylegan. The paper is called unpaired image-to-image translation using cycle-consistent adversarial networks. A problem for Pix2Pix was that it has to create paired training data for image translation. And the idea is to translate a model, means to generate a model that works for unpaired data collections. So before we had corresponding images, there was, for training, there was an edge image of a cat and a corresponding RGB image of a cat. But what do we do if we just have, let's say, a lot of nighttime images and then a lot of daytime images, but no correspondences? Or, as in this example, we have sunny beach photos and overcast beach photos. So we want to learn a translation from one class, say class X, to another class, let's call it class Y. So here's a visualization of paired training data versus unpaired training data. On the left, we see paired training data where we're always given images in two domains, but they're kind of corresponding. So the first edge image of a shoe corresponds to the first color image of a shoe. The second edge image of the boot corresponds to the color image of a boot, and so on. But with unpaired, we might simply be given a bunch of photographs of landscape and a bunch of paintings from landscapes, but there's absolutely no correspondence. So on top we see one of the interesting results where the authors were able to translate horses to zebras and zebras to horses even in a video. An important concept is cycle consistency loss, a concept that is now used in many other papers as well. So this is a general concept that is also used outside of deep learning. But the authors were really one of the first to find a very impressive way to use this concept. So the idea is that it's very difficult to judge a single translation, but it is possible to judge a translation from one domain to another and then back in the original domain. So starting with an image of, let's say, a horse, then we can use G to translate it into a zebra and F to translate it back into a horse. So after taking a horse, then translating into a zebra and then back, we would expect that the final result is similar to the horse image that we started with. Also, the other thing, I'm a bit suspicious, I guess it should be Y. Also, the other direction, so if you start with a zebra, translate to a horse, and then back to a zebra, should look similar to what you started with. So we have these two domains, X and Y, and we have translation networks, G and F, that are able to translate from one domain into the other. G translates from X to Y, and F translates from Y to X. Then we can have two discriminators, one to judge images that are supposedly in space X. So for us, let's just say this is the horse space, and then this is Y is the zebra space. So this dx is going to judge if something is looking like a real horse, and dy is going to judge if something is going to look like a real zebra. So if we start with some image X, then we can translate it with generator G into the zebra space, and then we can use the zebra discriminator to judge if this looks like a realistic zebra, and then we can translate back with F, and then we can get this x hat and check that this x hat is similar to x. So this is how the data is being processed on the top, but looking at from these two different spaces, we see that this blue point is transferred into y, and then y is transferred back, and we would hope that the two blue points are very similar to each other. This is the cycle consistency loss. Let's just ignore this for now and ask what happens if I only train the generator G by trying to translate horses to zebra and then judge if this looks like real or faked zebras. Then the network could basically ignore the input image. It could give you something that looks like a zebra, but that looks completely different than the input image you provide. In order to prevent the network from ignoring the input horse that you give it, the cycle consistency somewhat tries to make sure that the zebra that you generate will look different, will look similar to the horse. Because if it doesn't look similar, the idea is that it is difficult to translate the zebra back to a horse that looks similar, so that is this x hat that looks similar to the starting x. But then we also need to train this zebras being translated to horses and then back to zebras. So that's the same thing, just now we go the other direction. And then all of this is trained at the same time. Wasserstein-Gans are another really important paper, and Wasserstein-Gans introduce two things. They introduce a new loss function, and they also introduce the idea of regularization. That is a type of regularization that makes sure that the GAN is not able, or that the weights are not going to be too big. Let's look at this visualization down here. What this is, it's the plot of the loss functions of a DC GAN trained on the MNIST dataset. The green curve shows the generator error, and the blue curve shows the discriminator error, or loss. So these curves look quite crazy, and note that there can be these significant spikes as well. So GANs can be interpreted to minimize the Jansen-Shannon divergence, and the idea is somehow to bring a different type of metric into play here. And so instead of minimizing the GS divergence, the authors propose to use the Wasserstein or earth mover distance. All right. So you would have to look up some of the derivation, and we're not going to discuss the details here. So basic idea is just to switch the distances and obtain a more simplified loss function. One other thing that Wasserstein-Gans used to kind of regularize was some brute force clipping operation. And while that kind of works, it's not considered to be very elegant. So then there were some follow-up papers, for example, improved Wasserstein-Gans and improved Wasserstein-Gans. They came up with a better way of regularization. Again, we'll just do it at a high level. And what they do is they come up with this idea of a gradient penalty. Progressive growing of GANs was another milestone, and the milestone was inequality. For the first time, we saw results that were 1024 square, and the GAN that was being trained did generate quite a lot of examples that were of really high quality. So while the other GANs generated something that looked like faces, none of the faces were really, let's call them error-free, or, I mean, this is kind of very subjective how to exactly call it. I would maybe formulate it like this. If you look at it really quickly without analysis, the question is, can you, as a human observer, be fooled by something? And so some of these images that were generated by this paper, in contrast to previous papers, they would at least pass some simple test of being able to maybe fool a human. Also, one important thing is that using generative adversarial networks becomes a lot easier if faces or objects are presented in some aligned way. So, for example, having faces anywhere in the image, it's a lot more difficult for the GAN rather than if the face was actually being aligned. So what the authors do is they generate this special data set where faces are aligned. So, for example, this is an aligned face. They try to put the eyes and the face approximately in the middle, have not the size should not be too different, and then the improved training data is also a significant factor why the results improved. The architecture is built on WGAN GP, what we briefly showed in the previous slide, and another idea that the authors propose is to use progressive growing. That's what also gives the paper the title. Let's first look at these results. So, as promised, without some deep analysis, these images look really good, and they could be real photographs of real people. Of course, these images were cherry-picked. So generating a random image does not look that good. The latest GANs, for example, on this page, this person does not exist. So the follow-up work to this paper, you could almost generate a larger number of faces, and it will take a while until you find one that looks unrealistic. All right, let's look at progressive growing. We start at some resolution 4 × 4 pixels, and then we upsample to 1024 × 1024. So in the beginning, the generator generates 4 by 4 images, and the discriminator judges 4 by 4 images. Then, after some time of training, there will be another layer added to the generator and another layer to the discriminator. Okay, there might be multiple layers, just to illustrate the principle. And then both the generator and the discriminator are growing in a synchronized fashion until we have the full GAN shown here to the right, where the generator generates 1024 squared images and the discriminator judges them. This is the architecture. Maybe some interesting side remarks. The authors actually used nearest neighbor sampling in order to upscale images. The convolutional layers, shown in light blue, are 3 by 3 convolutions with stride 1 and same padding. Leaky ReLU is the chosen activation function. Another very interesting concept is that the authors used pixel normalization, which is some really brute force normalization. And the idea is that each pixel you just normalize by itself. So when you think of the image, for example, the image might be a 16 by 16 by 128 tensor, then each of the 16 times 16 pixels is a vector with 128 dimensions, and you just make this vector unit length. Stylegan is a further step to improved quality. The paper also introduces a new data set. Here are some examples. These are just examples shown in different resolution that can be generated by this architecture. There are also other things that can be done by modulating a style code and manipulating. Let's look at the architecture of Stylegan in some more detail. There are two parts. There is a mapping network on the left that is a new component, and then there is a synthesis network on the right that is very similar to how the Gans looked like since DC GAN. It's just convolutional layers and upsampling layers. So the network starts with a tensor that is 4 times 4 times 5, 12. Then we ignore some steps for now. Then there's going to be a convolutional 3 by 3 layer. Then there's some upsampling. Again, there's a convolutional layer. Then there's another convolutional layer. Again, some upsampling. And this is how the network progresses from 4 times 4 resolution to 1024 times 1024. But now the noise is not only, or the control is not only inserted in the beginning, but continuously as the network grows and grows and grows the image, there will be information injected using either some noise as shown to the right. This is really just some image noise. It has a particular form, so we'll ignore some of these details, but we'll spend some time just looking at this. Here, this is an adaptive instance normalization. That means that for each channel in a tensor in the network, we will remove the mean and standard deviation, as we already did many times in this course before. And then we will add our new mean and new standard deviation, but not as in other forms such as batch normalization. We really do it very similar to style transfer, where the mean and standard deviation are values that are provided by this mapping network. So this provides the control over the result. And the interesting thing is that just changing mean and standard deviation of tensors, channels in the network, is enough to fully control the result. So what we do here is we cannot just directly random sample and change the mean and standard deviation based on random samples. We will have to first bring this very random samples in a simple space. So I forgot exactly. I'll just, for now, let's just say this is 12-dimensional vector. We'll map it with this mapping network, which is a multi-layer perceptron, fully connected network. So we see there's just a bunch of linear layers that are used to map the Z codes that are in some simple space into this more complicated W space. And so these W's are also 512-dimensional, and they will control the instance normalizations. At the end, that means that each output image is controlled by one single 512-dimensional vector. There were some other changes made to the architecture. So after Stylegan, there was a revision made, Stylegan version 2, that modified how this instance normalization works in more detail. And there's another paper, training Gans with limited data, which makes some minor tweaks to the architecture, but mainly focuses on training Gans with limited data. That is, can we do some transfer learning for Gans, and can we use better data augmentation for GANs so that we don't need, let's say, 30,000 images, but that we can train with only maybe 1,000 images. Building on Stylegan, some members of our group have looked at this question: is it possible when you start with an image, can we find a W code, it's a slight modification of a W code, that corresponds to this image, and then use Stylegan to modify a given input image? So here are some examples of embedding well-known faces into the Stylegan latent space, that is, into the modified W space. After embedding existing images into the Stylegan latent space, it is possible to edit these images. And this is also the basis of Adobe's new product, the neural filters that can be used for face editing. While Stylegan is clearly the state-of-the-art for faces, BigGAN, and there's also some follow-up work, is the state-of-the-art for training on ImageNet. Another catch maybe is that there are some other autoregressive models now that claim to compete with GANs on ImageNet. I'm not 100% sure what the latest results are and which of these claims are really true, like who has really the claim to the best quality results. For this course, I would mainly sum it up as saying that BigGAN is how can you build a GAN. It's not entirely brute force, but how can you build a GAN if you had a lot of hardware laying around and you can really scale it up and you really try to generate a GAN that can handle a lot of data. And this paper, BigGAN, contains a lot of the architecture choices that the authors made to make it happen, the training on large datasets such as ImageNet. Let's just skip forward to some of these values here. So BigGAN has 355 million parameters to train 256 squared ImageNet images, and you need Google TPUs for the training. Quite a lot of them. Here are some results. Looks really fantastic. Finally, I would like to mention this paper, Few-Shot Adversarial Learning of Realistic Neural Talking Head Models, that is able to synthesize videos. So what you can do is give the network a few images of a person. So the network is pre-trained, but then you can give it a few images of a person, and that's enough for the network to then synthesize a video of the person talking. And the video is controlled by a landmark model of a face that can then control how the face acts, or how the face acts in